So calculations with thermal noise were quite simple, simply summing noise temperatures and summing noise powers, and quite straightforward. Understanding the only thing we have to understand is that the noise temperature of an amplifier is always referenced on its input. But everything else is straightforward, and we are summing noise powers because we have all impedances matched, and the signals are uncorrelated. And in this way, we can simply handle a chain of amplifiers. I corrected here the bandwidth to B to have the same marking on both on all drawings here. This is a very simple calculation to be done. Unfortunately, some engineers think it differently. All these calculations here always involve linear units. So we have linear units for the signal to noise ratio, for the powers, for the gains. Gains have in linear units. We do not have any logarithmic units here except for this Boltzmann spectral noise density of thermal power in dBm per hertz. This is the only logarithmic units we ever encounter here. But not all people think it this way. So many years ago, I think this is more than half a century ago, in the times of table communication, they introduced even another quantity for thermal noise, and this quantity was called noise figure. What is the definition of noise figure? The original definition is quite stupid, but we should understand its origins, and then it makes sense. If we look at the origins of this definition, it makes sense. So the noise figure is the degradation of the signal to noise ratio. We understand that at the input of an amplifier, we have a better signal to noise ratio at the input, and this signal to noise ratio degrades at the amplifier output. If we now calculate this thing, at the input we only have the noise coming from the antenna, so we have only the temperature of the antenna, and at the output we have both the antenna and the receiver. So if we calculate the signal to noise ratio at the input and the output, we see that this signal to noise ratio degrades. So this noise figure is always larger than 1. If we cancel out all the similar quantities, it's a quantity that is larger than 1. Now this definition makes no sense. Why it makes no sense? The noise figure should be a property of this amplifier here. F is a property of the amplifier in the same way as the noise temperature of this amplifier is a property of this amplifier. But this property of the amplifier is defined by the noise temperature of the antenna. And this noise temperature of the antenna may change. So how could the properties of an amplifier change by changing another component in the system? And this makes really no sense. The property of an amplifier cannot be a function of the antenna, because we can plug in another antenna, connect another antenna, and this thing will change, and the amplifier will not change in the time in between. So where this definition came from and why did it came from? Well, the reason was very simple. Say in the middle of the 20th century, where did this noise calculation apply? Such noise calculation. Such noise calculation applied in two cases. One case was that we have a cable, a lossy cable here, like a long coaxial cable line. And that lossy coaxial cable line has a very defined temperature, noise temperature. It's not an antenna, but still a coaxial cable at room temperature radiates as a black body at room temperature if its loss is large enough. So it's not TA, but it's T0 here. And if we are the other possible application for this calculation of noise were microwave point-to-point links, and with microwave point-to-point links the antenna is pointed into the next mountain with the next repeater station. And since this antenna is pointed into the ground, its noise temperature is again very close. Its antenna temperature is very close to the reference temperature, 290 Kelvin. So in this case, this definition of the noise figure makes sense, because it's temperature of the receiver divided here by the reference temperature, 290 Kelvin, and this is an agreed value upon. And this applies very well for cable communication. So for cable communication, we can use this equation. This figure here applies very well for microwave point-to-point links. So thinking about the middle of the 20th century, this equation was quite useful. Though wrong. The equation is wrong, but it was quite useful. And of course, there is a relation in the opposite direction. If we define the noise figure in this way, we can also define the noise temperature of the receiver just inverting this equation. Frequently, the noise figure is expressed not as a linear ratio, but is expressed as decibels with logarithmic units. Because noise figure talks about noise powers, it's a power ratio. We are using 10 times logarithm to the base 10 of the noise figure here. So in logarithmic units, usually the noise figure is expressed in logarithmic units, or vice versa. We can just take the exponent function of 10, appropriate exponent function, to calculate the receiver noise temperature from its noise figure. The noise figure, as I said, is always a degradation. The noise signal-to-noise ratio can only be degraded, so the noise figure is always larger than 1, and the noise figure in decibels is always larger than 0. Here I must explain a warning here. Many textbooks on electronic communication explain this thing here in the wrong way. We are going to see further details of this equation, why this is wrong, but on many occasions this equation is explained in the wrong way in many textbooks. So be very careful when considering other sources about this equation. I will explain later on this into detail. As I said, the noise figure is only another way of expressing the noise temperature, as we have selected the value for the reference temperature T0, and this is fixed, is selected, is defined. This is our reference temperature. Then there is a one-to-one relationship between the noise temperature and noise figure, or vice versa, noise temperature calculated from noise figure in decibels. So it does not bring really new information. The noise figure parameter is not telling us anything new. It's just causing confusion, having yet another measurement unit for the noise in the system. Where did this equation fail? Where this equation fails? Well, it happened quite quickly. This was around the middle of the 20th century, where we had cable communication and microwave point-to-point links. In both microwave to point-to-point links and cable communications, this TA is always close to T0. This equation fails when we have satellite communication. So just a few years later on, when communication satellites were introduced, this equation fails completely with satellites. So with satellites, this equation is no longer valid, and but it's still explained in the wrong way in many textbooks. So be very careful when considering textbooks, especially textbooks not dealing just with noise, dealing the electronics on the general. This equation may be explained in the wrong way. Let's see how can we rewrite this communication. There is a very popular nomograph to do these things. So noise temperature of the degrees in degrees Kelvin versus noise figure in decibel, and you see there is a one-to-one relationship. It's not really necessary to invent, and this nomograph is quite famous, quite used. Here still, in this nomograph, they are using the degree sign. Usually Kelvin is, we are used to write Kelvin without the degree sign, but here still there are degrees Kelvin for the noise temperature and noise figure. Of course, we have relationships in both directions, provided that we have the agreement, they follow the agreement of 290 Kelvin. So with this, using this nomograph, we can calculate, just right quickly say, if we have a 1 dB noise figure of our amplifier, this equals to 75 degrees Kelvin of noise temperature. If we have 120 dB 120 degrees of noise temperatures, this is 1.5 dB of noise figure. So it's very easy to use. And of course, this scale is expanded here on this nomograph, is expanded at this low noise figure, because this is where things are interested in satellite communications, and it's much more compressed here at the high noise figures, and the highest noise temperature is much more compressed. But it's a very useful nomograph when you have to do a calculation, just because of people using both units. People like to define the noise figure, like to use, say, data sheets of amplifiers, of transistors, define the noise figure. But for calculations, we need the noise temperature, and vice versa. Once we made our calculations, we have to convert everything back into noise figure. Let's see how do these things work. Now, the simplest, also not just how do these things work, what are the orders of magnitude here? The simplest example is a GSM phone, a mobile phone. A mobile phone has an omnidirectional antenna, and this omnidirectional antenna is seeing the environment of the phone. So its noise temperature is not far away from 290 Kelvin. It's mainly the environment. If we are using, say, in a room, the mobile phone, the antenna sees the walls of the room, and all the walls of the room are at room temperature, so there is not much new here. The question now is, what is the sensitivity of the receiver of the GSM phone? The sensitivity of the receiver, if we know that we need a signal-to-noise ratio, we will see this more when we will be dealing with modulations. So we need to demodulate a GSM signal, we need a signal-to-noise ratio of approximately 10 dB. In a bandwidth of 200 kilohertz for a GSM phone. And the amplifier, the noise figure of the amplifier is around 5 dB. So 5 dB, why it is not better? Because semiconductors can do it better. But we also have other components. We have an antenna switch between the receiver and transmitter. We have an antenna filter here. We also have requirements for the dynamic range for the distortion in this amplifier. So we cannot just optimize it for the noise figure. So 5 dB makes sense here. So what we do in our calculation, first we have to calculate the noise temperature out of the noise figure. And if we calculated this, we see that our receiver has around slightly more than 600 Kelvin noise temperature. We calculate the overall noise power, that's bandwidth times Boltzmann constant, times the sum of the temperatures, antenna plus amplifier, plus receiver, antenna plus receiver. So if we calculate this 200 kilohertz times the Boltzmann constant times the sum of our temperatures, we get 2.5 times 10 to the minus 15 watts. So this 10 to the minus 15 is something a little bit difficult to understand. But it becomes much more easier if we convert these figures into dBm. So the signal power has to be the noise power times the signal-to-noise ratio. We need a signal-to-noise ratio of at least 10. So 10 dB converted to a ratio is also 10. So 2.5 times 10 to the minus 15 multiplied by 10 is 2.5 times 10 to the minus 14 watts. Still 10 to the minus 14 watts does not tell much, But if we convert this into decibels per milliwatt, so signal power in dBm, decibels per 1 milliwatt of power. This is a dBm is a very common unit in radio communication and also in optical communication. dP watt would be the correct unit, but the correct unit, but dBm is very popular among engineers. This is minus 106 dBm. 106 dBm, minus 106 dBm, is the theoretical sensitivity of these receivers. And maybe I must say it immediately that many mobile phones achieve exactly this figure. This was the exact calculation we could do here. Now we can also do the simplified calculation using the noise figure here. Using the noise figure, we could do this simplified calculation. So how we do this simplified calculation? We can do it because the temperature of our antenna is close to the room temperature. We are using mobile phones in closed environments, so this is quite a good assumption. So now we can calculate the signal to noise, the noise power, the signal power on the receiver input as the signal to noise ratio in decibels plus the bandwidth in decibels times hertz. We can also express the bandwidth in decibels plus the kBT0 constant. We had this already before in the dBm per hertz of bandwidth plus the noise figure in dBs. So the noise figure is how much this amplifier actually degrades the noise figure. This thing only holds when we have the antenna temperature at the reference temperature. But the GSM phone is one of those cases when this thing works, and we can make this calculation. So express all quantities we need. We need kBT0. This is minus 174 dBm per hertz. 200 kilohertz converted into dBm per hertz is 53 dB per hertz. So now we make our calculation: 10 dB of signal to noise ratio, 53 dB per hertz of bandwidth, minus 174 dBm per hertz of noise spectral density, and 5 dB of noise figure, and we get the correct sensitivity of our receiver. The minimum input signals to our receiver is minus 106 dBm. Here we simply added, in our calculation, we simply added the noise figure, and we got everything correct. We got everything correct because of this antenna temperature that was just the right value here. This is not very common. This may not happen. And as I said before, the first problem was encountered with satellite communications. So with satellite communications, we are receiving a satellite. Our antenna is pointed to the cold sky. The antenna is receiving some noise from other objects, but these objects are outside the main beam of our antenna. So since they're outside the main beam of our antenna, their contribution is small. So the antenna temperature here is around 20 Kelvin. And we want to replace our old receiver that had a noise figure of 1 dB. Satellite TV receivers always have the noise figure printed on the package, with the new receiver that has half a dB of noise figure. So actually the change of the noise figure was just half a dB here. Does it make sense to replace the receiver to have just half a dB of improvement? Probably not. But actually we are not interested in the change of the noise figure in decibels. We are interested in a change in the difference of the signal to noise ratio, again expressed in dB. And this is 10 times logarithm of the ratio of the temperatures. The temperature in the first case was antenna plus noise temperature of the first receiver. In the second case, we have antenna temperature plus the temperature of the second receiver. We had two different receivers, same antenna. According to this example here, first receiver was 75 Kelvin, second receiver was 35 Kelvin. Antenna temperature is always held at 20 Kelvin. So 20 Kelvin plus 75 Kelvin, 20 Kelvin plus 35 Kelvin, we divide, we take the logarithm, and we obtain an improvement of the signal to noise ratio by 2.37 dB, almost 2.4 dB improvement. So for half a dB of change in the noise figure, we obtained a much better improvement of the signal to noise ratio. So here it really makes sense, because 2.4 dB of improvement in satellites. Signals from geostationary satellites are very stable. We usually are at the limit using the smallest possible antenna here, or we are at the edge of the coverage of the transmitting antenna on board the satellite. So this improvement comes in very handy, especially for digital TV, for satellite digital TV, where improvements make really a difference, especially if forward error correction is used in satellites. This may make difference with digital TV. It may make difference between no reception at all and perfect picture. So this thing really makes sense, but it's quite different from the change in the noise figure, which contradicts this expression here. So our change in the signal to noise ratio was not the noise figure here. Was not the change in the noise figure. So this is not the same. This is explained wrong in many textbooks, and this is an example why the textbooks don't hold. Those textbooks don't present the right result. Okay, this is one possibility when we have satellite reception. So artificial satellite communications immediately made this thing stupid or obsolete, this definition of the noise figure. But because this thing was quite popular, people resorted to these sensible definitions and knowing what they were doing. They were not calculating the signal to noise ratio, but they were calculating things against a lossy cable, or against an antenna pointed to the ground, or against a signal generator. A signal generator also has an attenuator on its output, and it is radiating noise at the room temperature. So this sensible definition also applies when we are using signal generators, say, to check our receivers. Yes, besides the satellite reception, there is also the opposite case. The opposite case is HF reception. HF receivers. Here I made a very simple example at 27 MHz for a citizen band radio transceiver. This is a very common item that can be bought. You may have heard with citizen band radio transceivers that this receiver, if the squelch is disabled, generates very little noise is heard from the loudspeaker when there is no antenna connected. And you can only hear the noise coming out of the loudspeaker of the citizen band radio transceiver when you connect the antenna. Why? This citizen band radio transceiver was using amplitude modulation. Some are also using FM, but with amplitude modulation, your noise is proportional to the power received from the antenna. And in the HF region, so below 30 MHz, the noise temperature is very large. The noise temperature of the sky, galactic noise, also some planets of the solar system, like Jupiter, is radiating lots of noise on HF. And in fact, this was the first noise discovered by Karl Jansky back in the beginning of the 20th century, and this was the beginning of the radio astronomy. So this noise is very large. In the HF range, Karl Jansky was making his experiments around 20 MHz, so his noise temperature was very large, and he detected this radiation. Of course, he was ignored by his supervisors, and radio astronomy only took took development decades later. What happens here? Now we have two different receivers, two different citizen band radios. One has a noise figure of 10 dB and the other has a noise figure of 5 dB. So the difference in the noise figure here is 5 dB. But what are the corresponding noise temperature? The noisier receiver is 2600 Kelvin and 600 Kelvin is the lower noise radio. But we have 100,000 Kelvin from the sky received by our antenna. So the change in the signal to noise ratio here is only proportional to the change of the sum of the noise temperatures in first case and in second case, and this difference is really small. This figure is really small. What does this tell? In the, say, before the Second World War and also in the Second World War, when most radios were operating at frequencies of 30 megahertz or below 30 megahertz, it was almost unimportant. The noise figure of the receiver noise was almost unimportant. It made no change in the final signal to noise ratio. So noise figure comes up only when microwaves come up. When microwave links, when cable communications over cables come up, then the noise figure makes sense, and then the receiver noise makes sense. And noise temperatures make sense. While at HF, noise temperatures, because of the high noise temperature of the sky, the noise temperatures of the radios used make very little sense. So this is just the opposite example as we had here. Here we had an example when this was very sensitive to the noise. Satellite TV was very sensitive to the noise figure, very big differences in the signal to noise ratio. While HF reception, big differences in the noise figure make no difference in the received signal to noise ratio. So here the quantity is really important. We still have to consider one final issue of chains, and here we only described a chain with amplifier blocks. So each amplifier had its own temperature, had its own gain. A very common example is also an attenuator. We also have attenuators in our chain. Where may these attenuators come from? They may come from a lossy antenna, an antenna that has a radiation efficiency less than 1 or a logarithm of the radiation efficiency less than 0. Maybe a lossy transmission line or even a longer coaxial cable where we have line amplifiers to restore the signal level on this coaxial cable. And this coaxial cable is also a lossy transmission cable. We may have bandpass filters. All real-world bandpass filters have some transmission loss. We want to have a low bandpass loss in the bandpass filter, but this is unfortunately not equal to 0. We still have some loss, and we may have passive components in our radio. We didn't discuss this thing yet. So we may have frequency mixers. Frequency mixers are maybe active, maybe passive mixers. In the case of passive mixers have a conversion loss that also translates into insertion loss here. What is the calculation now here? We have an attenuator in our line that is going to attenuate our signal by this factor A less than 1, or negative dB here. So signal gets attenuated. This attenuator also attenuates the noise temperature coming from the antenna. This antenna noise temperature is also attenuated by the attenuator. But the problem is that this attenuator, it's also radiating its own noise. An attenuator is a gray body, not really a black body. If we had infinite attenuation, so A equal to 0, then it would be a black body. It's not a black body, it's a gray body, but it is radiating at its own TR temperature of these resistors here. It's radiating noise. So now we have three sources of noise: antenna, attenuator, and receiver. and we have to make the calculations. So in order to stay consistent with the noise temperature, if the antenna noise temperature is attenuated by A, 1 minus A is the radiation of the attenuator. Because if A goes to 1, then this term should vanish, and if A goes to 0, then this term vanishes, and this becomes 1. So we should exactly see 1. So this is the only sensible contribution of the noise made by this attenuator. If we put all this into our calculation, we get quite a complex result. We have T antenna decreased by A, we have T resistor here, and we have T temperature of our receiver. And also the signal is attenuated by A. So if I try to cancel out now this A in the numerator and A in the denominator of this fraction here, I put just to simplify this equation, I divide both numerator and denominator with A, and I get this relationship here. Actually, what happens in this relationship? T Rx prime and F prime are the noise temperature, equivalent noise temperature and equivalent noise figure of the whole chain, the chain of the attenuator and amplifier. We see actually that the temperature of the receiver increases because A is less than 1. Our equivalent noise temperature of the receiver increases, and further we have the contribution of this term here, which is non-zero. So things will go bad because of this attenuator. This attenuator is really causing harm here, is damaging our signal-to-noise ratio. We can also transfer that to noise figures, and also for the noise figure F prime of the whole chain connection here also gets larger. If we think about the definition without the attenuator or with the attenuator, it gets very complicated. Now here we got a complicated equation that it's difficult to use. But there is a simplification. And the most frequent case is that this attenuator is located at room temperature. So all three resistors, R1, R2, and R3, are at room temperature. And if we put in our equation here, if we put TR is equal to T0, then this equation simplifies much. And we see that here minus 1 minus 1 disappears, and in the first term we have 1 over A and TRX over A times T0. So if I put in front this 1 minus A, if I put in front it, I get here just the noise figure of our receiver. So if the attenuator is at room temperature, then the noise figure of my amplifier degrades just by the factor A, and this is the simple part of the equation. So if the attenuator is at room temperature, it's very simple to do calculations. So the noise figure prime will be just the noise figure minus the attenuation. The attenuation is negative because the attenuation we are losing signal. So here really is plus some dB here. So the noise figure F prime in decibel is growing corresponding respect to the noise figure. So this is a very simple formula, and this very simple formula actually now it's an excuse for using this stupid unit noise figure. This unit here was just making our calculations complicated, but in the case of an attenuator, this noise figure actually simplifies our life, and this is when it is useful. Unfortunately, as soon as we have a chain of many components like here, we have to revert back from decibels back to linear units, back to temperatures to calculate the whole chain. So it's not a very good definition, but this is very useful. So if I have a receiver that has 5 dB noise figure and I have minus 2 dB of attenuation in the cable, then the whole noise figure of the whole connection will be 5 dB here, minus 2 dB is the whole, we get to 7 dB here. So it's a very simple calculation in many practical cases when we actually need these things. So there is yet another definition we need in the case of noise, and that's the G over T ratio, so the gain over temperature ratio of an antenna. So a receiving antenna is described by its gain, but it is also described by its antenna temperature here. And actually what we are interested in our link, we are interested to have the maximum signal to noise ratio at the output of our link. Say here was for example, I'm giving here satellite reception, because with satellite reception this is most important. We can calculate the free space link from the satellite using the Freeze equation. We did this with antennas, and we get the signal power. But we are not trying to maximize actually the signal power. We are trying to maximize the signal to noise ratio. And the signal to noise ratio is also dependent of the temperature of our antenna. Now, temperature of the receiver, this is constant. If we have selected a receiver with a certain receiver temperature with a certain noise figure, then this is fixed. But the antenna temperature may not be fixed. If this is a parabolic dish antenna, this noise temperature mainly comes from the spillover lobes, from the lobes caused by the spillover of the feed. These lobes that are actually collecting ground temperature, because the ground is at 290 kelvins compared to the 10 Kelvin of the free space. So if we were able to reduce the side lobes of this antenna, we could decrease the antenna temperature much. So with satellite reception, it makes sense to invest in the antenna temperature, have the lowest antenna temperature, even if we compromise a little bit the gain. So what we do over there, we under illuminate the dish so that we get less gain because the dish is under illuminated, but we have much less side lobes pointing into the soil. We have these side lobes, but these side lobes here are pointing into the cold sky, so that's not a problem. The side lobes given by the under illumination. The side lobes of the spillover, those that are collecting lots of power. So rewriting the ratio of these two antennas, P receiver divided by P noise, we have a term that depends on the transmitter, and we cannot do anything about the satellite. The satellite is there as it is. We have some figures that depend on the system, so the distance r, the wavelength, the Boltzmann constant, the bandwidth, so this is dependent on the system. And we have some parameters of the receiver, the receiving antenna gain, and the temperature of the antenna and the temperature of the receiver. So all these three figures depend on our receiving station. And usually in satellite communication it's common to specify not the size of the receiving antenna, not the antenna temperature, but to specify the G over T ratio, which is gain of the receiving antenna divided by antenna temperature and TRX. This is the minimum G over T that will provide us a useful signal to noise ratio at the output. G over T is frequently given in decibels. So decibels over Kelvin, and in order to cancel decibels, cancel Kelvin out of this ratio so that we can compute the logarithm, we need to multiply this with the constant 1 Kelvin here. So GRX, this is in linear units, not in decibels. Temperature is in Kelvin, and in order to cancel this Kelvin, we need the 1 Kelvin constant here to have GT over T in this dB per Kelvin. So this is the usual way to specify ground stations for satellites. This is the usual way. Finally, talking about all these figures, we have to find out how to measure these things, because we have to actually measure temperature of the antenna, temperature of the receiver. We have to measure these quantities because if we specify them, we have to prove that these figures are correct, and we have to measure them. How are we going to make measurements? There are several possibilities. I will only mention here the most popular one, and the most popular way is first, the devices we have. We have to measure all these devices we have. We have to measure their noise figure or their noise temperature. You see that with modern semiconductor devices, noise temperatures are quite low. They are in the range of room temperature or even less than room temperature. Noise figure is between 0.3 and 3 dB for present day semiconductor devices. In fact, the best laboratory devices, they do not even require liquid nitrogen to achieve 7 Kelvin of noise temperature. You can achieve 7 Kelvin even at room temperature with the best available transistors today. All these devices have pretty lots of gain. Devices have quite an amount of gain. So usually second stage is not that important. Second stage and further stages. So this equation does apply, but the contribution of the further stages, since g of each stage is large in linear units, it's very small. So they have plenty of gain usually in the region. There are some older devices that are quite noisy, like vacuum tubes. Vacuum tubes have a much higher noise figure. Why? Because the amplification process in a vacuum tube takes place between the cathode and the control grid, and the cathode is heated up to a few thousand Kelvin. So this thing is very warm inside. Even warmer are speed modulation tubes, electron beam speed modulation tubes like klystrons or traveling wave tubes. This provides plenty of gain, but unfortunately very high noise figure. Also, things of the past is the parametric amplifier using gallium arsenide varactors pumped with a millimeter wave pump, a much higher frequency oscillator pumping this varactor, and when we pump this gallium arsenide varactor, this varactor behaves as a negative resistor, very low noise negative resistance at microwave frequencies. So this is also thing of the past, thing of 50 years ago parametric amplifiers. But they could not do much better, or at the same room temperature, they could not do much better than modern semiconductors. So we are talking about the semiconductors. What we should be careful about semiconductors is that if we use not bare transistors, but if we are use already integrated amplifiers like microwave monolithic integrated circuit amplifiers, these amplifiers include feedback, regardless whether they are made of silicon or silicon germanium or indium gallium phosphide. Their feedback generates a much larger noise. So resistive feedback used in MMIC amplifiers provide quite a large amount of noise. Just to mention, the worst thing of all is to use an operational amplifier. Operational amplifiers have been optimized to have infinite input resistance, almost infinite, almost zero output resistance, and almost infinite gain. And what is the final result? An operational amplifier is extremely noisy. So operational amplifiers have a very large noise temperature, very large noise figures. So whenever low noise is in question, never use an operational amplifier. And even an MMIC amplifier, you may use it in the second stage, not in the first stage. In the first stage of your device should be a bare transistor with all matching circuits outside the transistor, all matching circuits made out of reactive components. No lossy feedback in this amplifier. So just to say, what can we do? What kind of noise can we receive? Can we get out of our receiver? So our receiver can be quite good, and we will have to measure this thing later on. Further, we have to learn, this is just as I mentioned, what to do if we have an impedance mismatch. In all our discussions here, you see always I have this remark, all impedance is matched to the ZK. Well, that's the ideal case. In the real world, our transistors, we can describe noise generated in a transistor amplifier with two independent noise sources, a voltage noise source and a current noise source. And these noise sources are completely independent of the linear parameters, linear scattering parameters describing the linear properties of this amplifier. So in order to get the best possible, the lowest possible noise out of these amplifiers, we have to perform the impedance matching not on the S parameters but on the noise parameters. There are three noise parameters. It's the minimum noise figure, is the optimum source reflection coefficient, so what should be the reflection coefficient of our antenna, or matching circuits we need here, and it's the noise resistance. This noise resistance tells us how fast the noise figure degrades as we move away with our reflection coefficient of the source from the optimum value, as far away as we move from the optimum. We have the formula here, we have the definition here. Some manufacturers are using this definition here. So of course we would like to get F-min, but F-min means tuning the noise source to gamma optimum. We cannot do that on all frequencies. But at least we can do calculation and see these noise parameters are sometimes published for some low noise devices, not always. We should understand that these noise parameters are independent of the S parameters. Noise parameters may require quite weird impedances here. A low noise amplifier typically has a negative input resistance, so it is actually reflecting more noise out to the antenna than it's receiving from the antenna, because its reflection coefficient, its input reflection coefficient, is larger than 1. Such an amplifier is potentially unstable, but we want the lowest noise, and we have to work out to get that lowest noise. This is very difficult to do. Just to mention that there are solutions when we have an impedance mismatch, when the source is not matched to 50 ohms and when our amplifier is also not matched to 50 ohms. There are solutions, but we should understand that a low noise amplifier may have other requirements. So we may have a requirement to always have the requirement to have the lowest possible noise, and we can sacrifice that. We can sacrifice the stability of this amplifier, so this amplifier will not be unconditionally stable. Finally, we have to measure things, and the usual way to measure our active device is the hot-cold method. There are other methods that can be done, but they are not as accurate and as straightforward as the hot-cold method. So our amplifier, because it is potentially unstable, it should always be matched to the system impedance. So these resistors here should be equal to the characteristic impedance. We should have equality here. Source should be exactly 50 ohm, and our amplifier should be matched to 50 ohms. But we have one cold resistor at a lower temperature T1 and one hot resistor at a warmer temperature T2. We switch between the two, and the difference between the two is just in the difference of the antenna temperature. The antenna temperature here is T1, here is T2. So we get two measurements, two powers at the output. And if we divide these two, we get the Y factor. The Y factor is the power ratio, noise power ratio we get at the output. We see here that the gain of the amplifier cancels out, the bandwidth of the filter also cancels out, and also the Boltzmann constant cancels out in this ratio. So we have only T1 plus TRX and T1 plus TRX and T2 plus TRX. So the Y factor is simply this ratio here. Y factor is usually expressed in decibels, is 10 times logarithm of this ratio. Okay, we can do the calculation back if we know the temperatures of our resistors. If we know the Y factor, we can calculate the temperature, the equivalent noise temperature of this amplifier. or its noise figure. We can calculate it from the Y factor. Here the Y factor is given in linear units. Decibels is usually what is displayed with an instrument, but linear units are used in our formulas here. What noise temperatures can we start with? We can start with different resistors. Of course, the simplest solution here is room temperature. We may heat a resistor or we may cool a resistor. A resistor at room temperature is an antenna into an absorber, oriented to an absorber at room temperature. So maybe an antenna oriented into green vegetation, especially pine trees are very good microwave absorbers, so we get the 290 Kelvin of temperature from pine trees. Also resistor at room temperature. We can cool our resistors to liquid nitrogen. We can go even cooler if our antenna is pointed into the cold sky, avoiding the sun and avoiding a few celestial noise sources. But we can also heat our resistor, say heat it with a light bulb. A filament of a light bulb is a resistor, and if we heat it, if we make this light bulb shine, its filament glow, we have it at maybe perhaps we can reach 2000 Kelvin. An ionized gas can also be used as a resistor, and this is around 10,000 Kelvin noise temperature. And finally, the most noisy device is an avalanche breakdown. An avalanche breakdown is very noisy. We have special diodes. They are just like stabilizer diodes built for avalanche breakdown that may provide us 1 million Kelvin of noise temperature. So our final figure today is how to measure these things. So this can be done in the lab, but it's cumbersome to having to operate this switch manually, to have two resistors at different temperatures. We would like to mechanize up this procedure here. That's the reason why we have a noise head with a built-in avalanche diode. Usually these noise have an 18 volt breakdown diode, so 28 volt plus a drop resistor, we get to the 18 volt of the noise diode head. Here we can get 1 million Kelvin for T2, while T1 is at room temperature at 290 Kelvin, so we may have we may obtain quite a high excess noise ratio, usually expressed in dB. If we want to calculate, we also have in our testing we have measurement receivers, and these measurement receivers allow us have a mixer, contain much additional gain in the IF amplifier, and contain a filter. So we can bring here just an amplifier without filters and with enough gain because we provide additional gain here. How do we make the measurement? We measure the Y factor here. The Y factor here we measure, but the Y factor contains also both the amplifier under test, the temperature, but also contains our test equipment, the temperature, noise temperature of our test equipment divided by the gain of this amplifier. So if we know the gain of our amplifier, if we know the noise temperature of our measurement receiver, this is all solved because this is all solved in the Y. This is all solved, so we can get the temperature of our receiver from this measurement if we invert this formula here, or the noise figure in dB if we know the gain of our measurement sample and if we know the temperature of the receiver. But we can do more. We can calibrate our receiver by connecting the diode head directly to the input of our receiver. So in this case we get equations 3 and 4. We measure these two powers, and when we connect our amplifier under test, we get equations 1 and 2. We can solve a system of 4 equations for 4 unknowns. Temperature Rx, this is what we are measuring. Gain of the receiver, if we don't know, it's welcome that we have it available. We can solve it for the temperature of our test receiver, and we can solve it for this unknown constant of our receiver. So we can characterize our receiver from these two equations. We can already calculate these two values here, and then we can plug in these values into first equations, connect our amplifier, and calculate the interesting parameters of this amplifier, not just its noise temperature but also its gain. So this is the noise figure meter is a very useful instrument, provided that we are able to use it, because there are several limitations. This excess noise ratio should not be nor too small nor too large, so we have quite limitations. It's not a universal instrument like the vector network analyzer. But still, the noise figure is a very useful instrument, not just to measuring the noise, but also to measuring other parameters in the system. So this is about noise, our lecture about noise. So next time, what we should do? Well, in all our discussion today, we always had bandpass filters. We had a bandpass filter. Here we have a bandpass filter. Here we have bandpass filters in the receivers. At the end of our chain, we always have bandpass filters. The next issue we have to solve is how to make a bandpass filter that actually matches our signal and filters away as much noise as possible. So we have to look at bandpass filters, and this will take us quite some time to actually make our communication. We looked at semiconductor devices, how much noise do they have, and semiconductor devices are okay. We have noise parameters of semiconductor devices, we know how to use this thing, but we need filters to make actually our link work. So the next step we have to look for in the next lecture is the bandpass filter. How do we make different bandpass, low pass, high pass, any kind of frequency filters we need using passive components. So this would complete our receiver, not yet our transmitter, because we have our other problems. But at least to complete our receiver, we need this yellow box here. We need it explained, and we have to do this next time.